Welcome, fellow explorers, to a voyage deep into the heart of the cosmos. A journey that stretches our imagination, challenges our understanding of reality, and dares us to question everything we thought we knew about the universe. I'm Dr. Alex Carter, and today we're embarking on a mind-bending exploration of black holes, the fabric of space, time, and the astonishing physics that underpins our reality. Grab your seat and prepare to be amazed. The cosmic enigma. What is a black hole? Imagine a region in space where the very laws of nature twist and warp into something almost beyond human comprehension. Black holes are not objects in the traditional sense. They are profound distortions in the fabric of space-time itself. Born from the remnants of massive stars, these cosmic phenomena represent nature's ultimate paradox. A place where gravity becomes so overwhelming that it warps the very structure of reality, swallowing everything that dares to venture too close. At the heart of a black hole lies a boundary known as the event horizon, a point of no return. Beyond this invisible line, the gravitational pull is so intense that not even light can escape. It's as if the cosmos has carved out an area where the rules we take for granted are completely rewritten. Picture a vast, turbulent ocean with a hidden whirlpool at its center. As waves and currents spiral inward, they are inexorably drawn toward an unseen vortex. In much the same way, matter and radiation caught in a black hole's pull are drawn relentlessly toward its core. Deep within this enigmatic region lies the singularity, a point where the density of matter becomes infinite and our current understanding of physics ceases to apply. The singularity is a mystery wrapped in an enigma. It challenges our conceptions of space, time, and causality. Here, the curvature of space-time is so extreme that the very concepts of before and after lose their meaning, leaving us with more questions than answers. Einstein's theory of general relativity provides the mathematical framework to describe these phenomena, revealing that mass and energy dictate the shape of space-time. Yet, black holes push these equations to their limits. They invite us to explore the boundaries of scientific knowledge, where quantum mechanics and gravity collide in a dance of contradictions and surprises. As we peer into these cosmic maelstroms, we are reminded that the universe is a far more dynamic and mysterious place than everyday experience might suggest. In this exploration, we will journey into the depths of these gravitational titans, examining their formation, their effects on the surrounding cosmos, and the astonishing phenomena that emerge at their fringes. Black holes, with their blend of awe-inspiring beauty and mind-bending physics, serve as the ultimate laboratories for testing our theories about the nature of reality. Prepare to challenge everything you thought you knew about space, time, and the very fabric of existence as we unravel the secrets of the cosmic enigma. Birth of a cosmic giant. The life and death of stars. Our journey into the cosmos begins with the brilliant lives of stars, the celestial furnaces that power galaxies and sculpt the universe. A star is born within vast cold clouds of gas and dust, where gravity gathers material until it ignites nuclear fusion at its core. In these early moments, a star enters a delicate equilibrium. The outward pressure generated by fusion reactions counterbalances the relentless pull of gravity. For millions, even billions of years, this balance keeps the star shining steadily. A beacon in the vast darkness of space. As time unfolds, however, the star's fuel, primarily hydrogen, begins to dwindle. The core contracts under gravity's grip, heating up and igniting the fusion of heavier elements like helium. This transition marks the beginning of a dramatic transformation. With each new element fused in its core, the star's inner workings grow more complex. Yet, this complexity carries a fatal flaw. When the star reaches the stage of fusing iron, no further energy is produced to counteract gravity. Unlike previous fusion reactions that released energy, the fusion of iron actually consumes energy, leaving the core unable to support the outer layers. At this pivotal moment, the balance tips catastrophically. The core collapses in a fraction of a second, and the outer layers are hurled into space in a brilliant supernova explosion. A cosmic fireworks display of unimaginable force. This explosion not only marks the death of the star, as it once was, but also seeds the universe with heavy elements that will form new stars, planets, and perhaps even the building blocks of life. For stars that are moderately massive, the collapse leaves behind a neutron star, a compact, dense remnant where matter is packed so tightly that a single teaspoon could weigh billions of tons. But for the most massive stars, gravity's overwhelming force drives the collapse even further, crushing the core into an infinitely dense point known as a singularity. This is the birth of a black hole, a cosmic giant whose gravitational pull is so intense that nothing, not even light, can escape its grasp. Thus, the death of a massive star gives rise to one of the universe's most enigmatic entities. In the aftermath of a supernova, a black hole emerges as a monument to both destruction and creation. A focal point where the laws of physics are pushed to their limits. The cycle of stellar birth, life, and death illustrates the dynamic and ever-changing tapestry of the cosmos, reminding us that even in endings, there is the seed of a new beginning. The event horizon, the ultimate point of no return. The event horizon is one of the most captivating and mysterious features of a black hole. It is not a physical surface, but rather an invisible boundary, marking the point beyond which nothing can escape the black hole's grasp, not even light. As matter and energy approach this critical threshold, they experience an extraordinary shift in behavior that challenges our understanding of time and space. Imagine drifting toward an unseen border where the familiar laws of physics begin to unravel. From the perspective of an external observer, as an object nears the event horizon, time appears to slow down dramatically. This time dilation effect, predicted by Einstein's theory of general relativity, creates a surreal scene. Objects seem to freeze in mid-motion, their final moments stretched out into eternity. To us, it appears as though the infalling matter never quite crosses the boundary, instead fading away into darkness as its light is increasingly redshifted. However, for the object itself, the journey past the event horizon is markedly different. In its own frame of reference, time continues to flow normally. There is no sudden jolt or visible barrier at the event horizon. Instead, the transition is seamless, almost imperceptible. Yet, once crossed, the object enters a realm where conventional concepts of space and time lose their meaning. Here, all paths inevitably lead to the singularity, a point of infinite density and gravitational pull where the known laws of physics break down. The event horizon is also key to understanding how black holes interact with their surroundings. It is the demarcation between the region of space-time that is causally connected to the rest of the universe, and the hidden interior where information is lost from external view. This boundary is dynamic, its size and shape determined by the mass, spin, and charge of the black hole. For supermassive black holes, the event horizon can extend over distances that dwarf our entire solar system, creating an immense sphere from which no signal or matter can escape. Moreover, the event horizon has profound implications for the nature of reality itself. It serves as a natural laboratory for testing the interplay between quantum mechanics and general relativity. The very fact that we cannot observe events beyond this boundary forces scientists to rethink how information is stored and preserved in the universe. This has led to revolutionary ideas, such as the holographic principle, which posits that all the information contained within a volume of space can be represented on its boundary. In essence, the event horizon is not just the edge of a black hole. It is a gateway to some of the most fundamental mysteries of the cosmos. It challenges our perceptions of time, space, and causality, inviting us to explore realms where our classical understanding of the universe gives way to the strange and fascinating world of extreme physics. Quantum whispers, Hawking radiation, and the quantum vacuum. Imagine for a moment that even the emptiest void in space is never truly empty. Instead, it seethes with tiny ephemeral fluctuations, a restless dance of energy that gives birth to particles for just a fleeting instant. This is the quantum vacuum, where uncertainty rules and even nothingness is alive with possibility. In this realm, particles and their corresponding antiparticles continually pop in and out of existence, only to vanish almost as quickly as they appear. Stephen Hawking, one of the most brilliant minds in modern physics, proposed a groundbreaking idea. Black holes, despite their reputation as cosmic sinkholes from which nothing can escape, might not be entirely black after all. At the edge of a black hole's event horizon, the quantum vacuum plays a subtle trick. Occasionally, a pair of virtual particles is born near this boundary. Under normal circumstances, these particle pairs would annihilate each other almost instantly. However, the extreme gravitational field of the black hole can sometimes tear them apart. One particle may be captured by the black hole, while the other escapes into space as real, detectable radiation. A phenomenon now known as Hawking radiation. This radiation is incredibly faint, but its implications are profound. Over unimaginable periods, as Hawking radiation leaks away tiny amounts of energy, a black hole will gradually lose mass and, in theory, eventually evaporate entirely. This challenges the age-old notion that nothing can ever escape a black hole's gravitational grip. It also forces us to confront the deep connection between gravity and quantum mechanics, a connection that remains one of the greatest puzzles in physics. Hawking's insights suggest that black holes are not eternal prisons of matter and energy. Instead, they participate in a cosmic balancing act, radiating away energy as dictated by the laws of quantum theory. This interplay between the quantum vacuum and the immense gravitational force near the event horizon creates a whisper of radiation that carries with it clues about the fundamental nature of space, time, and energy. Moreover, the study of Hawking radiation has opened up avenues for exploring a unified theory of quantum gravity. By examining how these quantum whispers emerge from the fabric of space-time, scientists hope to bridge the gap between Einstein's theory of general relativity and the probabilistic realm of quantum mechanics. In doing so, we edge closer to understanding not just the fate of black holes, but also the very foundations of our universe. A universe where even the void is a dynamic, ever-changing arena of cosmic possibility. The dance of destruction, accretion disks, and cosmic jets. As matter falls toward a black hole, it rarely plunges straight in. Instead, it spirals in, forming a luminous accretion disk, a swirling, flattened structure of gas and dust caught in a relentless gravitational embrace. In this cosmic ballet, the material in the disk is subjected to intense friction and gravitational forces that heat it to millions of degrees. As a result, the disk radiates energy across the electromagnetic spectrum, often outshining entire galaxies. The sheer brightness and dynamic activity of these disks offer us a glimpse into the extreme conditions that exist near black holes. Yet, the spectacle does not end there. Under the right conditions, magnetic fields generated by the swirling, electrically charged particles within the accretion disk become extraordinarily strong. These tangled magnetic fields can act like cosmic funnels, channeling some of the infalling material away from the black hole along its rotational axis. The result is the formation of powerful, collimated jets, narrow streams of matter and energy ejected at speeds approaching that of light. This phenomenon, sometimes associated with the Penrose process, allows energy to be extracted from the black hole's spin. The jets, which can extend for thousands or even millions of light years, punch through the surrounding interstellar medium, influencing the evolution of galaxies by stirring up cosmic material and triggering new rounds of star formation. They serve not only as spectacular beacons of high-energy physics, but also as critical tools for scientists who use their properties to probe the mysteries of gravity and magnetism under the most extreme conditions. In essence, the interplay between the blazing accretion disk and the forceful cosmic jets is a dance of destruction and creation. A dynamic, chaotic performance that reveals the true power of black holes and their profound impact on the structure and evolution of the universe. Space, time and motion. Einstein, relativity, and frame. Dragging Einstein's theory of general relativity revolutionized our understanding of the cosmos by showing that mass and energy are not isolated entities, but are woven into the very fabric of space-time. According to this groundbreaking theory, massive objects such as stars, planets, and especially black holes cause a curvature in space-time, a distortion that directs the motion of everything around them. When these massive objects rotate, they don't simply spin in space. They drag the very fabric of space-time along with them, an effect known as frame dragging. Imagine placing a spinning ball in a thick, viscous fluid. As the ball rotates, the fluid near its surface begins to swirl around in a similar motion. In the cosmos, a rotating black hole acts like that ball, its immense gravity and angular momentum causing the surrounding space-time to twist and spiral. This phenomenon is not just a theoretical curiosity, it has observable consequences. For example, frame dragging affects the paths of particles and light near the black hole, forcing them into orbits that mirror the twisting of space-time itself. This dynamic interplay means that the closer you get to a spinning black hole, the stronger the dragging effect becomes. In regions near the event horizon, space-time can be pulled along so violently that even objects trying to move in the opposite direction are swept along in the rotation. Such an extreme condition alters the behavior of matter in the accretion disk, potentially contributing to the powerful cosmic jets that we observe shooting out from the poles of active galaxies. Moreover, the concept of frame dragging extends beyond black holes. It's a fundamental prediction of relativity that has been confirmed around Earth with sensitive experiments, reminding us that even our home planet subtly drags space-time as it spins. In essence, frame dragging encapsulates the intimate relationship between mass, motion, and the very structure of the universe. A dance choreographed by gravity itself, continuously shaping the cosmos in ways that challenge and inspire our understanding. Beyond the horizon, wormholes, white holes, and parallel universes. Imagine a universe where the boundaries of space and time are not fixed limits, but doorways to realms beyond our immediate perception. Beyond the black hole's event horizon, theoretical physics invites us to explore exotic phenomena such as wormholes, white holes, and parallel universes. These concepts extend the familiar narrative of black holes into an even more mysterious and imaginative territory. Wormholes, sometimes referred to as Einstein-Rosen bridges, are theoretical tunnels that could connect distant regions of space-time. Picture them as shortcuts that bend the fabric of the universe, allowing travel between two far-flung points in an almost instantaneous manner. Though purely speculative at this stage, wormholes tantalize scientists and storytellers alike with the prospect of interstellar travel and even time travel. They challenge our conventional ideas of distance and causality, suggesting that the cosmos may be interlinked in ways that defy our everyday experiences. In stark contrast to black holes, which are cosmic sinks, white holes are conceived as their opposites, regions where matter and energy are expelled rather than absorbed. While a black hole's event horizon traps everything that crosses its threshold, a white hole theoretically prohibits any entry, only allowing matter to escape. Though no white holes have been definitively observed, their existence is mathematically consistent with general relativity. They offer a provocative glimpse into what might occur when the flow of time is reversed, turning the familiar concept of an end into a dazzling new beginning. Then, there are parallel universes, realms that may exist alongside our own, each with its own distinct version of reality. The idea of multiple universes arises from both quantum mechanics and cosmology, suggesting that our universe could be just one of many in a vast, possibly infinite multiverse. In some theoretical models, black holes or wormholes could serve as portals connecting these separate realities, allowing energy, matter, or even information to transfer between them. Such a possibility stretches our understanding of space, time, and identity, urging us to reconsider what it means for something to be real. Together, wormholes, white holes, and parallel universes represent the frontier where established physics meets the boundless possibilities of theoretical exploration. They compel us to ask profound questions about the nature of existence, the limits of scientific inquiry, and whether the universe is as compartmentalized as it appears. In venturing beyond the horizon, we are not merely peering into a cosmic void, we are challenging the very framework of our understanding. Opening our minds to a realm where the extraordinary is the norm and the boundaries of reality are redefined. Supermassive mysteries. the giants at the heart of galaxies. At the centers of nearly every galaxy lurk supermassive black holes, cosmic titans that can weigh millions to billions of times more than our Sun. These gargantuan objects have grown over eons by consuming stars, interstellar gas, dust, and even smaller black holes. Their relentless gravitational pull not only shapes the structure of their host galaxies, but also drives dynamic processes that influence star formation and galactic evolution. One of the most captivating examples is TON 618, a quasar powered by a black hole whose mass is so enormous that it dwarfs entire galaxies like the Milky Way. Despite their immense mass, supermassive black holes are remarkably compact. Their event horizons, the boundaries beyond which nothing can escape, span distances of only a few astronomical units, comparable to the scale of our solar system. This extraordinary density is a testament to the extreme gravitational forces that compress vast amounts of matter into an incredibly small volume. Studying these celestial giants offers us a unique window into the early universe. When astronomers observe distant quasars, they are looking back in time, capturing images of the cosmos as it was billions of years ago. The presence of supermassive black holes in such young galaxies raises profound questions. How did these objects grow so massive so quickly after the Big Bang? This mystery challenges our current models of cosmic evolution and suggests that the processes governing black hole growth and galaxy formation are deeply intertwined. Furthermore, the influence of a supermassive black hole extends far beyond its immediate vicinity. Its gravitational field governs the motion of nearby stars and gas, often leading to the creation of spectacular phenomena such as high-energy jets and luminous accretion disks. These jets, which can extend for thousands or even millions of light-years, blast material out into intergalactic space, impacting the evolution of entire galactic clusters. Supermassive black holes thus serve as natural laboratories for testing the limits of gravitational physics. They allow scientists to probe the interplay between matter, energy, and the curvature of space-time under the most extreme conditions. With advances in technology, such as the Event Horizon Telescope and upcoming next-generation observatories, researchers are beginning to unravel the secrets of these enigmatic giants, piecing together clues about the origins and fate of the universe. In essence, supermassive black holes are not merely the endpoints of stellar evolution. They are powerful architects of cosmic structure, continuously sculpting the galaxies around them with their unyielding gravity and profound mystery. The quantum puzzle, merging relativity with the micro-world. In the quest to understand the universe at its most fundamental level, scientists face one of the most profound challenges: reconciling the grand scales of general relativity with the minute realm of quantum mechanics. On one side, Einstein's general relativity describes how mass and energy warp the fabric of space-time, providing a remarkably successful picture of gravity at cosmic scales. On the other, quantum mechanics reveals a universe governed by probabilities where particles flicker into and out of existence in a seething, unpredictable dance. The collision of these two pillars of modern physics forms what many call the quantum puzzle. At the heart of this puzzle is the behavior of black holes. These enigmatic objects not only stretch space-time to its limits, but also serve as natural laboratories where the quantum and relativistic worlds intersect. Hawking's revolutionary prediction of black hole radiation, for example, arises from the interplay between quantum fluctuations and the intense gravitational fields near the event horizon. In this extreme environment, the ephemeral nature of the quantum vacuum comes into sharp focus, as virtual particles are given a chance to escape, hinting that even in the darkest corners of the universe, quantum mechanics leaves its mark. Yet, despite the elegance of these ideas, a comprehensive theory that unites quantum mechanics and general relativity remains elusive. Efforts such as string theory and loop quantum gravity strive to bridge the gap, proposing that space-time itself might be composed of tiny, discrete units, or vibrating strings. These approaches suggest that the smooth continuum described by relativity could be an emergent property arising from a fundamentally granular or multidimensional structure at the Planck scale. The implications are staggering. If space-time is indeed quantized, then the very fabric of reality is woven from these microscopic threads, and phenomena like black holes might be understood as macroscopic manifestations of underlying quantum processes. This search for unification is not merely an academic pursuit. It holds the promise of resolving long-standing paradoxes, such as the information loss paradox associated with black holes, and might ultimately provide insight into the origin and fate of the universe itself. By merging the cosmic with the quantum, physicists hope to unlock a deeper understanding of reality, one that transcends our current paradigms and challenges the very limits of human knowledge. In this relentless pursuit, every new theoretical breakthrough and experimental hint draws us closer to a unified theory, where the mysteries of the micro and the vastness of the cosmos are finally reconciled. In the swirling interplay between science and philosophy, black holes challenge our deepest beliefs about reality and perception. Beyond their measurable gravitational might and astronomical phenomena, these cosmic enigmas compel us to question the nature of existence itself. They force us to confront a universe where the familiar boundaries of space and time dissolve, urging us to consider whether our everyday experiences capture the true essence of reality, or merely a shadow of a deeper, hidden truth. Our conventional understanding of the world is built on predictable patterns, clear causality, and objects with defined properties. Yet, when faced with the extreme conditions near a black hole, these certainties crumble. Time dilates and space warps in such ways that our everyday intuition no longer applies. This unsettling divergence from the norm invites a profound philosophical inquiry. If our sensory perceptions are so dramatically altered in extreme environments, could it be that what we perceive as real is simply an emergent phenomenon, a projection shaped by the limits of our observation? Modern theories like the holographic principle and quantum uncertainty further blur the line between appearance and reality. They suggest that the universe might be fundamentally interconnected, with all matter and energy emerging from a more basic, underlying fabric of space-time. In this framework, our perceived world could be akin to a vast, intricate tapestry, woven from the collective vibrations of quantum fields, a tapestry where every thread holds the potential to reshape our understanding of what is truly real. Black holes, with their enigmatic event horizons and perplexing singularities, also challenge our notions of time. As objects approach these boundaries, time itself seems to slow and distort, raising the possibility that time may not be an absolute constant, but rather an emergent property born from the complex interactions of the cosmos. This realization forces us to reconsider the nature of causality and the very structure of existence. Ultimately, the philosophical frontier beckons us to expand our minds and embrace uncertainty. It encourages us to ponder that reality may be far more fluid and multifaceted than our everyday experience suggests. A mysterious, ever-evolving puzzle that continues to inspire both scientific exploration and philosophical reflection. In the modern era of astronomy, the challenge of observing black holes has driven technological innovation and theoretical breakthroughs alike. Although black holes themselves emit no light, their profound influence on surrounding matter provides us with indirect but compelling evidence of their existence. Through the study of accretion disks, gravitational lensing, and high-energy emissions, scientists have developed ingenious methods to probe these mysterious objects and unlock their secrets. Recent advances, such as the Event Horizon Telescope, EHT, have pushed the boundaries of our observational capabilities. By linking radio telescopes across the globe, the EHT creates a virtual Earth-sized dish, capable of capturing images of the shadow of a black hole against the backdrop of its glowing accretion disk. This monumental achievement has not only provided us with the first-ever image of a black hole, but also confirmed key predictions of Einstein's general relativity, offering a direct glimpse into the warped fabric of space-time around these cosmic giants. Moreover, astronomers are continually refining techniques to study the dynamics of matter falling into black holes. Observations across the electromagnetic spectrum, from X-rays to radio waves, allow researchers to analyze the behavior of plasma swirling at near-light speeds. These detailed studies help us understand how gravitational forces, magnetic fields, and quantum effects interact in the extreme environments near an event horizon. But the quest to observe the unobservable does not end there. Gravitational wave detectors, like LIGO and Virgo, have opened a new window onto the universe by capturing ripples in space-time produced by cataclysmic events, such as black hole mergers. These faint vibrations provide independent confirmation of black hole collisions, offering valuable insights into their masses, spins, and even the rate at which they merge. Gravitational wave astronomy is rapidly evolving, promising to reveal more about the hidden population of black holes and the violent processes that shape galaxies. Furthermore, theoretical models are being continuously updated and refined in light of these observational discoveries. Each new data point helps bridge the gap between what we can see and what we theorize, inspiring innovative experiments and missions aimed at capturing even subtler signals. With the advent of next-generation observatories and more sensitive instruments, the frontiers of black hole research are expanding, promising to unravel mysteries that have puzzled scientists for decades. In essence, observing the unobservable is an ever-evolving challenge that drives the cutting edge of astrophysics. It not only tests our technological limits, but also deepens our understanding of the universe, pushing us to reconcile the predictions of theory with the astonishing reality of the cosmos. Imagine the universe as an expansive symphony, where every star, planet, and black hole contributes its own unique note to an awe-inspiring cosmic melody. In this grand performance, the forces of nature, gravity, electromagnetism, and quantum mechanics come together to compose an intricate score that unfolds over billions of years. Every ripple in space-time, every burst of light, and every wave of gravitational energy plays a part in this celestial orchestra, creating a harmonious yet dynamic interplay that governs the cosmos. At the heart of this symphony lies the interplay between order and chaos. Galaxies rotate like majestic, swirling galaxies of sound, their stars acting as individual instruments that create vibrant chords. Black holes, often thought of as cosmic silences, paradoxically add depth and contrast. Their immense gravitational pull shapes the rhythm of matter and energy around them, while their accretion disks and powerful jets provide crescendos that echo across intergalactic distances. These dramatic episodes punctuate the otherwise steady hum of the universe, reminding us that even in darkness, there is beauty and structure. The universe's melody is not static. It evolves over time, with new themes emerging as stars are born, live their brilliant lives, and eventually fade away. The echoes of ancient supernovae mix with the gentle vibrations of cosmic background radiation, forming a soundtrack that is both timeless and ever-changing. In this cosmic symphony, every element is interconnected. The very fabric of space-time vibrates with energy, suggesting that even what we perceive as empty space is alive with potential. Ultimately, the universe as a cosmic symphony invites us to listen deeply to the mysteries of existence, a constant, dynamic interplay of forces that challenges us to explore, imagine, and find our place within this grand orchestral masterpiece. As we draw the curtain on this cosmic journey, we are left with a profound realization. The universe is not a static, easily decipherable entity, but rather a dynamic tapestry woven with mystery, wonder, and endless possibilities. The exploration of black holes, quantum phenomena, and the grand structure of space-time challenges our most basic assumptions, inviting us to rethink the very fabric of reality. Each discovery not only deepens our understanding, but also expands the boundaries of what we deem possible, urging us to embrace the unknown with both curiosity and humility. Throughout our journey, we have seen how the interplay between gravity and quantum mechanics reveals a cosmos that is both beautifully intricate and wildly unpredictable. Black holes, those enigmatic celestial titans, serve as both the engines of cosmic creation and the harbingers of destruction, pushing the limits of physics and igniting our imagination. They remind us that even in the most extreme conditions, there exists a hidden order, a symphony of forces that speaks to the unity of the universe. Yet, for all that we have uncovered, the more we learn, the more questions arise. The vast unknown remains an open invitation for future generations of scientists, philosophers, and dreamers. It is in this ever-expanding realm of mystery that innovation is born, where each unanswered question becomes a spark for exploration. The universe, with its countless enigmas, teaches us that uncertainty is not a void to be feared, but a fertile ground where creativity and discovery can flourish. So let us continue to push forward, to question, to observe, and to imagine. In the face of the unknown, we find the courage to redefine our understanding of existence. As we step into tomorrow, may we carry with us the spirit of inquiry and the resolve to explore the cosmic mysteries that still lie ahead. A journey that is as much about discovering the universe as it is about discovering ourselves. Thank you for joining me on this incredible journey into the depths of space and time. As we continue to explore the dark corners of the universe, remember that each discovery not only illuminates the mysteries of black holes, but also reveals new insights into the nature of our own existence. Until next time, keep your curiosity alive and your eyes turned toward the stars.